Far below the restless shimmer of the surface, where light begins to thin and temperature gradients settle into layered bands, a great white shark holds position in near stillness. From above, the ocean appears open and indifferent. But beneath the brightness lies a vertical battlefield defined by physics rather than spectacle. The shark does not patrol aimlessly. It studies silhouettes. A seal resting at the surface casts a shifting shadow downward, distorted by waves and refracted sunlight. That shadow is enough. In this realm, vision is not simply sight, but contrast recognition. The pale belly of the shark blends seamlessly with the glow of the surface when viewed from below, while its darker dorsal side dissolves into the deep when seen from above. This counter-shading is not aesthetic camouflage, but a calculated erasure of identity, an evolutionary refinement that reduces the probability of detection during the most critical seconds of approach. The great white is not merely a predator. It is a projectile waiting for alignment. The attack begins not with speed, but with restraint. Muscular contractions remain minimal as the shark angles its body vertically beneath the target. Its torpedo-shaped form, sculpted by millions of years of hydrodynamic optimization, minimizes turbulence and drag. The pectoral fins act as subtle stabilizers, adjusting micro-angles to maintain trajectory without announcing motion through pressure waves. Every unnecessary movement would ripple upward, and seals are exquisitely sensitive to disturbances. The ocean, in these moments, behaves like a pressure sensor grid. Even slight changes in water displacement can warn prey. To compensate, the shark relies on its lateral line system, a network of fluid-filled canals along its flanks, capable of detecting vibrations produced by paddling limbs above. Combined with acute vision adapted for low-light contrast, this sensory array allows the predator to map its victim from below, even when direct visibility fluctuates with passing clouds or surface chop. When the geometry is correct, the stillness fractures into acceleration. The great white's caudal fin, a powerful crescent of muscle and cartilage, drives downward strokes that convert stored potential into explosive thrust. The shark's red muscle fibers, built for sustained cruising, give way to bursts powered by white muscle fibers, specialized for rapid anaerobic output. In a matter of heartbeats, velocity multiplies. Water that once flowed quietly around its body now compresses and peels away in turbulent vortices. The shark becomes a rising missile, not metaphorically but mechanically. Its mass, often exceeding a metric ton, transforms into momentum directed vertically. The seal above, buoyed by blubber and surface tension, is suspended in a zone of vulnerability it cannot perceive from beneath. The breach itself is not incidental. It is the culmination of calculated hydrodynamics. As the shark nears the surface, it does not slow. Instead, it converts kinetic energy into vertical displacement, punching through the boundary layer between water and air. The impact alone can be catastrophic. Studies of high-speed predation events have shown that the collision force generated by a full-bodied breach is sufficient to disorient or fracture the rib cage of a seal before teeth fully engage. The prey's equilibrium collapses under sudden acceleration, much like a terrestrial animal struck by a high-velocity vehicle. In these seconds, the brutality is not in the bite, but in the physics. Shock, not puncture, determines survival. The ocean erupts in a column of spray and white foam as the shark and seal break into open air, gravity briefly suspended while momentum dictates trajectory. This aerial phase, often lasting only a few seconds, reveals the paradox of marine predation. A creature engineered for water temporarily defies it, using the very resistance of the ocean to generate lift. The breach is costly in energy, but the payoff is efficiency. If the seal is incapacitated by impact, the subsequent bite is not a prolonged struggle, but an act of retrieval. Serrated triangular teeth, arranged in conveyor belt fashion within the jaws, shear through blubber and bone with minimal hesitation. The first bite may not be for immediate consumption. Instead, the shark often releases, allowing the wounded seal to bleed while it circles back. This behavior reduces risk of counterattack and conserves energy, a strategy rooted in cost-benefit calculations shaped by evolutionary pressures. A large prey item represents both caloric gain and potential injury. The shark's method prioritizes minimizing harm to itself. The great white's oil-rich liver plays a subtle yet critical role in this assault. Comprising a significant portion of its internal mass, the liver is filled with low-density lipids that provide buoyancy without the need for a swim bladder, which sharks lack. This buoyancy system reduces the energetic cost of maintaining vertical positioning before the strike. It also assists in stabilizing the shark during ascent, allowing fine control over pitch and roll as it aligns with the prey. By lowering overall density, the liver contributes to the smooth transition from stealth hover to vertical launch. Evolution has converted metabolic storage into a mechanical advantage. Temperature regulation adds another layer of sophistication. Unlike many fish that match ambient water temperatures, great whites exhibit regional endothermy, maintaining warmer muscle temperatures through a countercurrent heat exchange system known as the rata mirabile. Warm muscles contract more efficiently, generating greater force during rapid bursts. In cooler waters, this internal thermoregulation ensures that acceleration remains uncompromised. The shark's ability to sustain high-performance movement in varied climates expands its hunting range and increases the likelihood of successful ambush in temperate seal colonies. What appears as a singular explosive event is in fact supported by circulatory engineering that preserves muscle readiness even in cold currents. The ecological implications of this hunting strategy ripple outward. By targeting seals, great whites regulate pinniped populations, indirectly influencing fish stocks and coastal ecosystems. Seals are efficient predators of schooling fish, and unchecked populations could disrupt trophic balance. The shark's brutality therefore functions within a broader regulatory framework. Predation is not random violence, but a selective pressure that shapes prey behavior. Seal colonies in regions frequented by great whites alter haul-out patterns, spending less time near steep underwater drop-offs where vertical attacks are possible. Some populations modify group formations, increasing vigilance and reducing solitary swimming. The presence of the shark alters not just numbers, but movement patterns, distributing ecological pressure across space. From the seal's perspective, the threat is largely invisible until eruption. The surface environment provides false security. Light refracts and masks upward silhouettes, while the bright sky blinds downward vision. The ocean's surface becomes a one-way mirror. This asymmetry defines the success of the Polaris-style attack. The prey scans horizontally, anticipating lateral pursuit, but the danger comes from below, where visual distortion obscures the rising mass. By the time hydrodynamic disturbance reaches the seal's sensory threshold, acceleration has already closed the gap. The assault is not a chase, but a detonation from beneath. Energy economics further underscore the strategy's efficiency. High-speed breaches are metabolically expensive, yet the caloric density of seal blubber justifies the expenditure. A successful kill can sustain a great white for weeks, reducing the need for frequent hunting. This feast-and-fast cycle aligns with the shark's migratory patterns, which span vast oceanic distances between feeding grounds and breeding areas. Satellite tagging has revealed that some individuals travel thousands of kilometers annually, timing their movements with seasonal prey abundance. The Polaris attack, therefore, is embedded within a larger migratory choreography dictated by ocean currents, temperature gradients, and prey distribution. The aftermath of a breach is often misinterpreted as chaotic feeding frenzy, but the reality is more measured. Great whites are typically solitary hunters, and while multiple individuals may converge on abundant prey sites, cooperative hunting of the kind seen in orcas is absent. Instead, hierarchy emerges through size and confidence. Larger individuals dominate access to carcasses, minimizing conflict through posturing rather than sustained combat. This social dynamic reduces injury risk and maintains individual fitness. Brutality here is individualistic, executed with precision rather than communal orchestration. The surface disturbance eventually settles. Foam dissipates. Seabirds circle, drawn by scent and fragments. Beneath the calming water, the shark's body temperature remains elevated, muscles gradually returning to cruising rhythm. The violent vertical strike gives way to horizontal glide. Blood disperses in plumes, feeding smaller scavengers, and initiating a cascade of nutrient redistribution. In this sense, the breach is not merely an act of predation, but a moment that injects concentrated energy into the surrounding ecosystem. What begins as shock and trauma becomes sustenance for a hierarchy of organisms, from fish to invertebrates to microbes. The Polaris attack exemplifies how evolution refines brutality into efficiency. The great white does not rely on prolonged pursuit or intricate trapping mechanisms. Its method condenses the kill into a single upward explosion, leveraging mass, velocity, camouflage, thermoregulation, and buoyancy into a unified weapon. The seal never sees the full shape of the predator. It experiences only the sudden collapse of stability as water turns to air and momentum overwhelms instinct. In that fraction of time between stillness and impact, the ocean reveals its vertical dimension as a domain of surprise, where survival depends on understanding not just who hunts, but how physics itself can be shaped into an instrument of execution. On a shallow tropical reef where sunlight fractures into shifting mosaics across coral ridges and sand channels, the violence is often small enough to escape notice. Parrotfish grind limestone into powder, wrasses flicker between coral heads, and waves pulse gently over the reef crest. Beneath a ledge no wider than a human forearm, a mantis shrimp waits inside a burrow it has engineered from rubble and compacted sediment. Its eyes, mounted on stalks and capable of independent rotation, scan in overlapping arcs, tracking polarization patterns and subtle movement that most animals cannot perceive. To the untrained observer, this shrimp appears ornamental, its body painted in electric greens and blues, segmented like an armored toy. Yet within this compact exoskeleton lies one of the most extreme mechanical systems in the natural world, a biological device that transforms stored energy into a detonation measured not in spectacle, but in physics. The mantis shrimp's weapon is not its claw in the conventional sense, but a highly specialized raptorial appendage shaped like a hammer. Unlike the pincers of a lobster or crab that rely primarily on muscular contraction for crushing force, this appendage operates through a latch-mediated spring mechanism that amplifies power beyond what muscle alone could produce. Inside the limb, elastic structures composed of chitin and mineralized cuticles store energy when the shrimp contracts its powerful flexor muscles. A saddle-shaped structure within the exoskeleton acts as a compression spring, bending under tension. For a moment, everything is held in place by a microscopic latch. The shrimp appears still, poised at the entrance of its burrow, watching a small crab edge closer in search of algae or detritus. That stillness is deceptive. Within the limb, potential energy builds like a drawn bowstring held at full tension. When the latch releases, the stored energy converts almost instantaneously into motion. The raptorial appendage accelerates forward with a speed that rivals the fastest projectiles engineered by humans. Measured in controlled experiments, the striking limb can reach velocities exceeding tens of meters per second within a fraction of a second, generating accelerations that would subject most biological tissues to catastrophic stress. In terms of scale, the appendage moves faster relative to its size than many bullets fired from small-caliber firearms. The force delivered at the point of impact is concentrated onto a small dactyl club, reinforced with layers of mineralized material arranged in a helicoidal pattern. This arrangement dissipates stress and prevents fracture, allowing the shrimp to strike repeatedly without shattering its own weapon. The club's architecture has inspired material scientists seeking to design impact-resistant composites because it balances hardness with flexibility in a way that prevents crack propagation. The initial collision between club and prey is devastating in its own right. Shells fracture, carapaces collapse, and the internal organs of crabs or snails are disrupted by blunt trauma. Yet the mantis shrimp's strike does not end at contact. The speed of the appendage through water creates a sudden drop in pressure behind it, forming a cavitation bubble. Cavitation occurs when local pressure falls below the vapor pressure of water, causing the liquid to vaporize and form a bubble. In propellers and ship hulls, cavitation is often a destructive nuisance, eroding metal surfaces over time. In the mantis shrimp's strike, cavitation is weaponized. As the bubble collapses in the milliseconds following formation, it generates intense localized heat and pressure. Temperatures inside the collapsing bubble can reach levels comparable to the surface of the sun, albeit for an infinitesimal duration and within a microscopic space. The implosion produces a shock wave and even a brief flash of light known as sonoluminescence, a phenomenon rarely observed in natural systems. The prey, therefore, experiences a double assault. First, the mechanical impact crushes or stuns. Second, the collapsing cavitation bubble produces a secondary shock wave that can rupture tissues and exacerbate internal damage. In some documented cases, the cavitation bubble collapses directly against the prey's body, even if the physical club misses by a narrow margin. The shock wave alone can be sufficient to incapacitate small organisms. This layered mechanism means that the mantis shrimp does not rely solely on precise contact. The surrounding water becomes part of the weapon, transmitting force outward in a radial burst. The reef itself seems to participate in the detonation as sediment lifts and tiny air pockets shimmer in the wake of impact. Such destructive capacity raises questions about control. How does the mantis shrimp avoid injuring itself with each strike? The answer lies in both structural reinforcement and neural precision. The saddle-shaped spring and club are composed of highly ordered microstructures that distribute stress across multiple layers. Cracks that begin at the surface are deflected by changes in fiber orientation, preventing catastrophic failure. Additionally, the shrimp times its strikes carefully. It does not swing indiscriminately, but waits for prey to approach within a narrow range, often just beyond the threshold of its burrow. This ambush strategy reduces the need for pursuit and minimizes exposure to larger predators. The shrimp's burrow serves as both fortress and firing position. From within, it can retreat instantly if threatened by fish that might prey upon it in turn. The ecological context of this strike is equally significant. Coral reefs are competitive environments where hard-shelled invertebrates dominate many niches. By cracking open snails and crabs that graze on algae or scavenge detritus, mantis shrimp influence the composition of benthic communities. Their predation can reduce populations of certain herbivores, indirectly affecting algal growth and coral health. In this sense, the sonic strike reverberates beyond individual prey items. It shapes micro-ecosystems, redistributing energy locked within calcium carbonate shells into forms accessible to scavengers and microbes. Fragments left behind attract smaller organisms, creating localized feeding events that ripple outward through the food web. The mantis shrimp's eyes add another layer of complexity to this predatory system. Each eye contains multiple photoreceptor types capable of detecting polarized light and a wide range of wavelengths. While the exact extent of their color discrimination remains debated, their visual apparatus allows them to perceive contrast and motion with remarkable acuity. In the dynamic lighting conditions of shallow reefs, where wave action produces flickering shadows, such sensitivity aids in detecting the subtle movement of prey against complex backgrounds. The shrimp can also gauge distance accurately, an essential skill when timing a strike that unfolds in mere milliseconds. Miscalculation would waste energy and expose the shrimp to retaliation from defensive claws or spines. Thermoregulation in tropical waters may seem trivial compared to polar seas, yet temperature influences metabolic rate and muscle performance. Warmer water accelerates biochemical reactions, enabling faster contraction of the muscles that load the spring mechanism. However, elevated temperatures also increase metabolic demand, requiring efficient foraging to sustain energy balance. The mantis shrimp's ability to deliver decisive strikes reduces prolonged chases and conserves energy. In this balance between expenditure and reward, the physics of the strike align with ecological necessity. Reproduction and territoriality further shape the use of this weapon. Some mantis shrimp species form monogamous pairs that share burrows, coordinating defense against intruders. In territorial disputes, the same appendage used for hunting may be employed in ritualized combat with conspecifics. Strikes are sometimes directed at the reinforced exoskeleton of rivals rather than at vulnerable soft tissue, suggesting a form of measured aggression designed to assert dominance without lethal consequence. Even here, the mechanics of the club dictate social structure. Individuals with larger or more resilient appendages may secure superior burrows, influencing reproductive success. It is tempting to describe the mantis shrimp as excessive in its destructive capacity, as though nature over-engineered a small crustacean for dramatic effect. Yet the reef is an arms race, where shells thicken and claws strengthen across generations. Snails evolve heavier armor, crabs develop harder carapaces. The mantis shrimp responds with enhanced spring mechanics and reinforced clubs. This evolutionary escalation illustrates how physical laws constrain and shape biological innovation. The shrimp cannot defy hydrodynamics, but it exploits them to amplify force. Water, often perceived as a dampening medium, becomes a conduit for shock. After the strike, fragments of shell drift downward, settling among coral rubble. The mantis shrimp drags its subdued prey into the burrow, where it methodically consumes the soft tissues within. Outside, the reef resumes its rhythm. Fish resume grazing. Currents resume their flow. Yet within the quiet architecture of the burrow, the chemistry of cavitation and the mechanics of elastic recoil have transformed a moment of stillness into an explosion measured in microseconds. The mantis shrimp's sonic strike stands as a reminder that in the ocean, brutality need not be large to be profound. It can be contained within a limb scarcely longer than a finger, where biomechanics and extreme physics converge to turn water itself into a weapon. The Antarctic wind moves across the pack ice in long, unbroken currents, sculpting the surface into ridges and plates that drift slowly with the tide. From above, the ice appears solid and protective, a floating continent of safety for seals that haul themselves onto its pale crust to rest, molt, and nurse their young. Beneath that frozen platform, however, the water is in constant motion, threaded with currents that carry both nutrients and hunters. In these sub-zero seas, a pod of orcas approaches not as solitary predators, but as a coordinated unit, their black and white bodies slicing just below the surface with deliberate restraint. They are not searching blindly. They are calculating angles, distances, and the structural weakness of ice that from the outside seems immovable. In this environment, survival hinges not only on strength but on collective strategy, and the orca has refined cooperation into an instrument of siege. The seal resting above senses little at first. Its primary defense is elevation, the simple geometry of distance between itself and the water. On ice, it is agile enough to shuffle toward cracks and plunge away if threatened by terrestrial predators. But the ice flow is not anchored. It drifts and flexes, its underside scalloped by meltwater and currents. Orcas understand this instability intimately. As the pod assembles beneath the flow, individuals align themselves side by side, their dorsal fins cutting faint shadows just under the surface. They communicate through bursts of clicks and pulsed calls that travel efficiently in cold, dense water. These vocalizations are not random chatter. They are precise acoustic signals that coordinate movement. The pod's matriarch often initiates the maneuver, drawing on knowledge acquired over decades and transmitted through generations. In these societies, culture is not an abstract concept, but a survival mechanism. Young orcas observe and rehearse wave-washing techniques for years before mastering them, imprinting patterns of timing and positioning that define their group's hunting identity. The attack begins with synchronization rather than speed. Several orcas swim in a tight line formation, accelerating in unison toward the edge of the flow. Their massive bodies displace water forward, creating a low swell that builds as they approach. Unlike a random wave produced by wind, this surge is directional and focused. The orcas adjust their depth and spacing so that the crest of water converges at a precise point along the ice margin. As they pass beneath the flow's lip, they angle upward slightly, amplifying the upward thrust of water. The resulting wave rolls across the surface, destabilizing the seal's footing. In some cases, the pod repeats this maneuver several times, each pass weakening the seal's position and eroding the ice's structural integrity. The process resembles naval siege tactics more than brute predation, with the hunters reshaping their environment to force the prey into a vulnerable medium. When the seal loses traction and slides into the water, the immediate danger is not necessarily a crushing bite, but a sudden shift from solid ground to liquid instability. Orcas are powerful swimmers, capable of bursts of speed that outmatch a seal's escape attempts, yet the initial objective is often disorientation rather than instant capture. The water churns with black and white bodies that circle tightly, cutting off retreat paths. The seal attempts to dive, but repeated lunges by different pod members push it back toward the surface, where oxygen demand accelerates. The orca's coordination ensures that the seal expends energy at a rate it cannot sustain. Exhaustion sets in rapidly in polar waters, where hypothermia compounds stress. Seals rely on thick blubber for insulation, yet prolonged submersion under pursuit elevates metabolic demand. As muscle glycogen depletes, swimming efficiency declines. In many cases, the prey succumbs to fatigue and cold before a decisive bite is delivered. The brutality here is methodical and controlled. Orcas possess formidable jaws, but in wave washing they deploy patience as their primary weapon. This strategy minimizes risk of injury to the pod and maximizes caloric return by ensuring the prey cannot mount a prolonged struggle. Unlike the explosive breach of a solitary shark, this is communal attrition. Each orca contributes to the outcome, and roles may shift fluidly within the group. Some individuals specialize in generating waves, while others position themselves to intercept fleeing seals. Calves remain slightly behind, observing and learning the choreography. The hunt becomes a classroom as much as a battlefield, embedding knowledge into the next generation's neural pathways. Orca culture varies remarkably across regions, underscoring that wave washing is not a universal trait, but a learned behavior specific to certain populations. In Antarctic waters, this technique is refined to target seals on ice, while other orca groups elsewhere employ entirely different strategies, such as intentional stranding on beaches to capture sea lions or cooperative herding of fish into tight bait balls. These divergent methods reflect distinct ecological contexts and prey types, illustrating that orcas adapt culturally as well as biologically. Their brains, among the largest relative to body size in the animal kingdom, support complex social structures and long-term memory. Matriarchs may lead pods for decades, guiding migration routes that align with seasonal prey abundance and sea ice dynamics. In the Antarctic, the timing of wave washing correlates with seal pupping seasons and ice formation patterns, ensuring that energy expenditure aligns with maximum nutritional gain. The acoustic landscape beneath the ice adds another dimension to the hunt. Sound travels faster and farther in cold water, enabling orcas to coordinate even when visual contact is limited by ice cover. Echolocation clicks bounce off the underside of floes, mapping their thickness and contour. By interpreting these returning echoes, orcas can assess whether a flow is thin enough to fracture or stable enough to require multiple waves. This capacity transforms the frozen surface into a three-dimensional tactical map. The orcas do not merely react, they analyze and adjust. In some documented instances, pods have been observed creating waves from multiple angles to induce rotational instability, effectively spinning smaller flows and throwing seals into the sea. Such precision suggests an understanding of cause and effect rooted in repeated practice and collective memory. The ecological consequences of wave washing extend beyond individual hunts. By preying on seals, orcas influence pinniped population dynamics and indirectly affect fish stocks and krill distribution. Seals are significant consumers of fish and squid, and their numbers can shape local marine ecosystems. Orcas, positioned at the apex of this trophic hierarchy, help regulate these interactions. Their presence also modifies seal behavior, encouraging more cautious use of ice and altering haul-out patterns. In years when sea ice coverage is reduced due to climate fluctuations, seals may cluster on fewer stable platforms, potentially increasing vulnerability to coordinated attacks. Thus, environmental change interacts with predation strategies in complex feedback loops. Thermoregulation plays a crucial role in this polar theater. Orcas maintain high internal body temperatures through thick blubber layers and countercurrent heat exchange systems that minimize heat loss in extremities. This physiological resilience allows prolonged hunting in frigid waters where other predators might fatigue. The seal, though insulated, cannot sustain extended chases without significant metabolic cost. The pod's collective endurance becomes an advantage, as individuals rotate positions during pursuit, distributing effort and maintaining group stamina. Such rotation resembles the relays of endurance athletes, though here the stakes are survival rather than sport. As the hunt concludes, the pod's coordination shifts from pursuit to consumption. Orcas often share prey within the group, reinforcing social bonds and ensuring that even younger members receive nourishment. The carcass is dismembered efficiently, with adults tearing off sections while calves feed nearby. In some cases, specific parts of the seal, such as energy-rich blubber, are prioritized. This selective feeding maximizes caloric intake and aligns with the orca's high metabolic demands. What began as a siege ends as communal sustenance, binding the pod through both cooperation and reward. The ice floe, now stripped of its occupant, drifts silently once more, bearing faint scratches where claws struggled for purchase. Above, the wind resumes its sculpting, indifferent to the violence that unfolded beneath. Below, the orcas move on, their silhouettes merging into the dark water beyond the pack ice. The hunt leaves no permanent scar on the frozen landscape, yet its impact resonates through the ecosystem. In this polar realm, intelligence and teamwork transform the ocean into an instrument of controlled force. Wave washing is not an eruption of chaos, but a demonstration of calculated drowning, where the prey's fate is sealed by coordinated motion and inherited knowledge. The brutality lies not in spectacle but in precision, in the understanding that the environment itself can be weaponized when minds operate in concert beneath the ice. Above the reef slope, where sunlight pours through clear tropical water in long, slanting shafts, a school of silvery fish moves as a single organism. Thousands of bodies pivot in synchronized arcs, each individual reacting to the subtle pressure changes created by its neighbors. The school breathes, expands, tightens, and contracts in response to currents and distant shadows. Safety here is statistical. The strategy relies on confusion, on presenting so many flashing flanks that a predator cannot isolate a single target. The water column becomes a living mirror, scattering reflected light in every direction. Within this shimmering chaos, perception is everything. A fish that reacts a fraction too late becomes a weak link, and the school will close ranks without hesitation, sealing the gap as though nothing had happened. At the periphery of this moving constellation, a long, slender form hovers almost invisibly. The barracuda does not thrash or announce its presence. It aligns itself parallel to the school, its body suspended with minimal fin movement. From a distance, it appears less like an animal and more like an extension of the water itself, a narrow band of shadow broken only by the faint glint of scales. Its shape is unmistakably aerodynamic, tapering from a pointed snout to a forked tail built for explosive acceleration. If one were to trace its silhouette against the refracted light, it would resemble a javelin poised in mid-air, balanced for release. The barracuda's musculature, composed of powerful lateral muscle blocks segmented along its flanks, stores potential energy for a burst that will last mere seconds, but determine the outcome of the encounter. What distinguishes the barracuda's approach is not only speed, but manipulation of optics. Its scales are coated in guanine crystals that reflect ambient light with a metallic sheen. In the shifting brightness of shallow water, these reflections fragment and blend with the flickering flashes of the schooling fish. The predator effectively camouflages itself within the very signal the school relies upon for cohesion. When the fish glance outward, they see brightness and motion, but not the defined outline of danger. Refraction at the water's surface further distorts shapes, bending lines and stretching forms unpredictably. The barracuda positions itself to exploit these distortions, often approaching from angles where sunlight strikes directly across its body, enhancing the illusion that it is simply another streak of brightness. The moment of attack begins with alignment rather than pursuit. The barracuda narrows its body angle, tightening its pectoral fins against its sides to reduce drag. Its gill covers press flush as it primes its caudal fin for propulsion. In the next instant, muscle contractions ripple backward along its spine, transferring force into the tail, which lashes side to side with astonishing acceleration. The water parts around the predator as it surges forward, transforming from suspended blade to projectile. Within fractions of a second, velocity increases to levels that overwhelm the reaction time of the schooling fish. Their lateral line systems detect pressure changes, but the signal arrives almost simultaneously with impact. The school splits in a flash of panic. Thousands of bodies scatter outward, creating a hollow channel where the barracuda's path cleaves through. Yet the predator does not aim at the densest cluster. Instead, it targets the moment of fragmentation, when individuals are briefly isolated from the protective mass. This strategy relies on understanding the behavior of collective prey. The barracuda does not simply chase, it disrupts. By striking at the edge or slicing through the center, it induces chaos that exposes a single fish for a fraction of time long enough to secure capture. The brutality lies in this exploitation of social cohesion. The very mechanism that provides safety becomes the vulnerability. Upon contact, the barracuda's jaws snap shut with precision. Its teeth, long and needle-like, are angled slightly backward, forming a cage that prevents backward escape. Unlike predators that crush, the barracuda impales. The teeth puncture soft tissue and grip firmly, ensuring that even if the fish thrashes violently, withdrawal is nearly impossible. The narrow spacing between teeth prevents prey from slipping sideways, while the elongated canines pierce through muscle with minimal resistance. In many cases, the first bite is lethal due to trauma and blood loss. Even if the fish remains conscious for a brief interval, its escape capacity is nullified by the arrangement of those dagger-like structures. Hydrodynamics amplify the effectiveness of this method. Because the barracuda's body is streamlined to minimize turbulence, it can maintain a straight trajectory without significant deviation during acceleration. This stability ensures that energy is not wasted in corrective maneuvers. The predator does not need to turn sharply. It selects its line of attack before accelerating and commits fully. Such commitment may appear reckless, yet it reflects evolutionary refinement. A predator that hesitates loses the advantage of surprise. The barracuda's strategy is built on certainty in its own mechanics. The ecological context of ram feeding reveals deeper implications. Schooling fish such as sardines and anchovies occupy critical positions in the marine food web, converting planktonic productivity into biomass accessible to larger predators. By thinning these schools, barracudas regulate population density and influence the distribution of prey species across reef systems. Their presence shapes schooling behavior, encouraging tighter formations and heightened vigilance. In regions where barracuda populations decline due to overfishing, shifts in prey dynamics can cascade through the ecosystem, altering predator-prey balances and even affecting coral health indirectly through changes in herbivorous fish populations. The barracuda's physiology supports repeated bursts of high-speed pursuit. Its muscle fibers are adapted for rapid contraction, fueled by anaerobic metabolism that generates power quickly but requires recovery intervals. After a strike, the predator often slows and drifts, allowing metabolic byproducts to clear before attempting another attack. This rhythm of explosion and glide defines its hunting pattern. Unlike endurance hunters that rely on sustained pursuit, the barracuda embodies short-range lethality. The ocean becomes a series of calculated dashes rather than a continuous chase. Visual acuity further enhances this method. Barracudas possess large eyes relative to their head size, granting them keen binocular vision in clear water. Their retinas are adapted to detect movement and contrast, essential for isolating prey against a bright reflective backdrop. While their reflective scales aid in camouflage, their own vision must cut through glare and shifting light patterns. The predator operates in an environment where optical illusions abound, yet it navigates them with precision, distinguishing genuine targets from the chaotic sparkle of the school. Occasionally, barracudas are observed shadowing larger animals such as reef sharks or divers, drawn by disturbances that may flush prey into open water. This opportunistic behavior underscores their adaptability. They are not strictly bound to solitary ambush, but can integrate into dynamic feeding events when circumstances favor rapid strikes. Even in these scenarios, their defining trait remains velocity combined with deception. They hover at the periphery, waiting for a moment when confusion peaks. The aftermath of a successful ram feeding is abrupt. The school regroups almost instantly, closing the void left by the captured fish. Within seconds, the pattern of synchronized motion resumes as though the interruption were negligible. Yet the impact resonates through the prey population. Survivors that experience the near miss exhibit tighter spacing and heightened responsiveness in subsequent movements. Predation events thus shape behavior over time, reinforcing schooling strategies while simultaneously revealing their limits. As currents sweep across the reef and sunlight shifts toward the horizon, the barracuda resumes its suspended posture, body aligned with the flow. It appears once more as a slender shadow among flickers of light, indistinguishable from the water's own movement. Its existence is defined not by prolonged struggle, but by sudden, decisive intrusion. The violence is swift and nearly silent, a collision of muscle, optics, and hydrodynamics that leaves little trace beyond a momentary flash of dispersing scales. In the realm of ram feeding, speed is not merely an advantage, but a weapon sharpened by physics. And deception is not theatrical, but woven into the very structure of the predator's skin. The river looks harmless at first glance. Its surface carries a slow brown sheen, reflecting mangrove roots and low-hanging branches that lean inward as if trying to listen to the current. Fresh water pushes outward from inland rain and underground springs, meeting the sea in a shifting estuary where salinity rises and falls with the tide. Juvenile fish cluster along submerged tree trunks, and wading birds step carefully through the shallows, stabbing at small crustaceans stirred by the flow. The atmosphere feels transitional rather than dangerous, a boundary between two worlds where salt gives way to silt. In such places, most marine predators hesitate. Their physiology binds them to the chemistry of the ocean, and their bodies are tuned to salt. Yet beneath the opaque water, moving with deliberate calm, is a shark that ignores this boundary entirely. The bull shark does not advertise its presence with a dorsal fin slicing clean blue water. In rivers and estuaries, visibility is often limited to a few body lengths at best. The water carries tannins, suspended sediment, and organic debris that absorb light and obscure silhouettes. In this low visibility world, senses beyond sight take precedence. The bull shark's lateral line system registers minute vibrations, tracing the erratic pulse of struggling prey. Its electroreceptors detect faint electrical fields generated by muscle contractions, even when the animal itself is hidden in murk. Here, camouflage is less about color and more about invisibility through chemistry. The shark's gray back and pale belly are less important than its ability to navigate in darkness, guided by sensory arrays that operate independently of light. What makes this predator extraordinary is not only its appetite, but its tolerance for fresh water. Most sharks are bound to saltwater environments because their bodies maintain internal salt concentrations that balance with the surrounding sea. Osmoregulation, the process of maintaining stable internal chemistry despite external fluctuations, defines the limits of their habitat. Bull sharks, however, possess a suite of physiological adaptations that allow them to cross that invisible chemical barrier. Their kidneys adjust the concentration of urea and other solutes in their bloodstream, preventing excessive water influx when entering fresh water. Specialized rectal glands, typically responsible for excreting excess salt in marine sharks, reduce their output in low salinity conditions. Hormonal regulation shifts to alter ion transport across gill membranes, ensuring that sodium and chloride levels remain within survivable bounds. The transition from sea to river is not a simple matter of swimming upstream. As the bull shark moves into progressively fresher water, its body begins a complex recalibration. In the ocean, its blood contains elevated levels of urea to counterbalance the high salt concentration outside. In fresh water, retaining that same concentration would cause water to flood its tissues. The shark therefore reduces internal urea concentration and increases urine production to expel excess water. Its kidneys enlarge relative to many other shark species, equipped to handle this metabolic burden. These adjustments require energy and time, which is why bull sharks often occupy estuaries, where salinity fluctuates gradually, rather than abruptly leaping from open ocean into purely freshwater systems. Yet once acclimated, they can travel far inland, sometimes hundreds of miles upriver, entering habitats where prey assumes immunity from marine predators. This capacity transforms geography into a weapon. In coastal waters, fish and mammals anticipate sharks. They have evolved schooling behaviors, migration patterns, and vigilance strategies suited to open seas. In rivers, those same species may behave differently. Juvenile fish use freshwater nurseries as refuges from oceanic predators, exploiting the lower salinity as a shield. Manatees and river dolphins share these channels, as do terrestrial mammals that wade or swim across to reach feeding grounds. The bull shark's presence disrupts this assumed sanctuary. It is comparable to a large terrestrial predator capable of entering fortified urban environments undetected, bypassing barriers that others cannot cross. The unpredictability lies not only in when it strikes, but in where it chooses to hunt. The bull shark's body is built for close quarters. Unlike the streamlined elegance of open ocean specialists, it possesses a stockier frame, with a broad head and powerful jaws suited for short bursts of force rather than extended pursuit. In turbid rivers, where maneuverability matters more than speed, this compact build proves advantageous. The shark often patrols near drop-offs, submerged logs, and sandbanks where prey congregates. Its attacks are sudden and direct. In murky water, the prey may detect a pressure change only moments before impact. The psychological brutality of such an encounter is profound, particularly for species accustomed to safety in shallow freshwater habitats. The strike is swift, often involving a single bite followed by a retreat, as the shark allows blood loss to weaken the victim before returning. Juvenile bull sharks frequently use freshwater systems as nurseries. These young individuals, smaller and more vulnerable to larger marine predators, benefit from reduced competition and predation pressure inland. The estuary becomes both training ground and refuge. Within these brackish zones, young sharks hone hunting techniques on smaller fish and crustaceans, gradually building strength before venturing into open sea. This life cycle reflects a complex interplay between physiology and ecology. Freshwater tolerance is not merely an opportunistic trait, but a strategic adaptation embedded in reproductive success. By raising offspring in chemically distinct environments, bull sharks reduce mortality and increase the likelihood of reaching maturity. Thermoregulation also influences their distribution. Rivers can experience greater temperature fluctuations than oceans, warming quickly under tropical sun and cooling rapidly during seasonal shifts. Bull sharks tolerate a broad temperature range, but their metabolic efficiency peaks within certain thresholds. Seasonal migrations often correspond to temperature changes and prey availability. During warmer months, they may venture deeper inland, following schools of fish that move upriver to spawn. As temperatures drop, they return to coastal waters where thermal conditions stabilize. This dynamic movement underscores the importance of environmental cues in shaping predatory behavior. In some regions, bull sharks have been documented interacting with entirely freshwater ecosystems, coexisting with species that evolved in isolation from marine predators. These encounters reveal how a single adaptable predator can alter community structure. Fish that previously grazed openly may adopt tighter schooling or seek refuge in denser vegetation. Terrestrial animals crossing rivers may become more cautious, adjusting behavior based on seasonal patterns of shark presence. The ripple effect of this predator's adaptability extends far beyond individual kills, reshaping ecological relationships. Human encounters with bull sharks often stem from this unpredictability. Rivers and estuaries are frequently sites of recreation, fishing, and transport. The murkiness that conceals the shark also obscures it from human awareness. Unlike clear coastal waters where dorsal fins may be visible, riverine habitats offer no warning. The shark's strike is not driven by malice but by sensory misinterpretation. Electrical fields generated by splashing limbs or struggling fish can trigger investigative bites. In such moments, the line between prey and intruder blurs. The bull shark's evolutionary toolkit does not distinguish intention. It responds to stimuli that historically signaled opportunity. Yet within this narrative of unpredictability lies a deeper evolutionary logic. The bull shark's success is rooted in flexibility. It occupies ecological niches inaccessible to many other large predators, reducing competition and expanding its hunting grounds. Its capacity to traverse chemical gradients mirrors the resilience required in fluctuating environments. As climate change alters salinity patterns and river flows, species capable of adapting physiologically may hold advantages. Bull sharks exemplify this adaptability, thriving in habitats that oscillate between salt and fresh with each tide. The estuary at dusk grows quieter as birds retreat and fish descend into deeper channels. The surface appears calm, disturbed only by drifting leaves and the faint swirl of current. Beneath, the bull shark moves with measured intent, body aligned with the flow, senses tuned to vibration and electric impulse. It does not need clear water or open horizons. Its domain includes shadowed river bends and muddy deltas where other apex predators cannot follow. In these transitional waters, the illusion of safety dissolves. The brutality of the bull shark lies not in spectacle, but in location. It strikes where confidence is highest, where the assumption of refuge is strongest. In doing so, it reminds the ecosystem that boundaries are not always barriers, and that the most formidable hunters are often those that ignore the lines others believe to be absolute. The reef wall appears still from a distance, its surface carved by time into ledges and crevices that shelter countless lives. Sponges inflate like breathing lungs, sea fans lean into the current, and small wrasses weave between coral branches in search of parasites. Yet within one narrow fissure, no wider than a human wrist, a pair of eyes reflects the filtered blue light with a steady, unblinking focus. A moray eel lies coiled inside the stone architecture, its elongated body folded in muscular loops that seem too dense for the space it occupies. Only the head protrudes slightly, mouth opening and closing in slow rhythm. To an untrained observer, this repetitive motion may appear threatening, as though the eel is baring its teeth in perpetual aggression. In reality, the movement is a necessity. Moray eels lack the opercular pumping system that many fish use to move water across their gills. Instead, they must open and close their mouths to ventilate, drawing oxygenated water inward in a process that resembles a silent, measured breath. The mouth itself is lined with recurved teeth, slender and needle-like, angled backward to prevent prey from slipping free. The first impression is one of jagged geometry, a living trap concealed within rock. Yet what makes the moray eel uniquely formidable lies not in this visible set of jaws, but in a second, hidden mechanism that waits behind it. Deep within the throat rests a pair of pharyngeal jaws, a structure derived from modified gill arches that in most fish assist with food processing but remain relatively static. In morays, evolution has repurposed this internal apparatus into a mobile grasping device capable of lunging forward into the mouth cavity. It is an adaptation so visually startling that it often invites comparison to science fiction creatures, yet its function is grounded in biomechanics, shaped by the constraints of a narrow, reef-bound life. A small fish drifts too close to the crevice, drawn perhaps by algae growing along the coral surface. In the dynamic ecosystem of the reef, proximity to structure offers both protection and risk. Many small fish rely on coral branches and rocky overhangs as refuges from open water predators. The moray eel exploits this assumption. Its coloration blends with surrounding stone, mottled patterns echoing the textures of sponge and coral. When it strikes, the movement is rapid but controlled. The eel lunges outward, jaws snapping shut around the midsection of the fish. In that instant, the outer teeth secure purchase, but the challenge of predation in confined space becomes apparent. Unlike predatory fish that rely on suction feeding to draw prey inward, moray eels lack the broad, expandable buccal cavity necessary to generate significant negative pressure. Their elongated skull and reduced opercular opening limit the effectiveness of suction. Instead, they have evolved a different solution. Once the outer jaws close, the pharyngeal jaws surge forward from the throat, propelled by specialized muscles attached to elongated bones that allow remarkable extension. These inner jaws slide along the floor of the mouth, reach the captured prey, and clamp down with a second set of teeth. In a coordinated motion, they retract backward, pulling the prey deeper into the esophagus. The action is swift and precise, a mechanical relay that converts initial capture into inescapable ingestion. For slippery prey such as fish coated in mucus or scaled with smooth armor, this mechanism eliminates the possibility of wriggling free. Even if the prey attempts to brace against the crevice walls, the backward-facing teeth and inward traction prevent reversal. The brutality lies in inevitability. Once the first bite connects, retreat becomes mechanically impossible. The evolutionary advantage of this adaptation is intimately tied to habitat. Coral reefs are structurally complex environments filled with narrow passageways where maneuverability is limited. Moray eels spend much of their lives within these confined spaces, rarely venturing far into open water. Their elongated bodies, lacking the rigid pectoral fins of many fish, allow them to snake through crevices with minimal resistance. However, this serpentine build restricts the ability to create strong suction. The pharyngeal jaws compensate for that limitation, ensuring that prey captured within the reef labyrinth cannot exploit the eel's structural constraints to escape. In essence, the eel has externalized part of the swallowing process into a dynamic grasping tool, converting a feeding weakness into a decisive advantage. This feeding strategy also reduces the need for prolonged struggle. In the tight confines of a reef crevice, violent thrashing could expose the eel to injury from sharp coral or from larger predators attracted by commotion. By securing prey quickly and drawing it inward with minimal external movement, the eel conserves energy and minimizes risk. The pharyngeal jaws function almost like a conveyor mechanism, transferring prey from the threshold of capture to the digestive tract in a controlled sequence. Such efficiency reflects evolutionary pressure to optimize feeding within spatially restricted habitats. The reef community responds to the presence of moray eels in subtle ways. Cleaner shrimp and small fish often approach the eel's mouth, picking parasites from its teeth and gill openings in a mutualistic interaction that highlights the complexity of ecological relationships. During these cleaning sessions, the eel remains relatively still, tolerating the intrusion of tiny organisms into the very jaws that moments earlier secured prey. This contrast between cooperative stillness and predatory precision illustrates how behavior shifts with context. The same anatomy capable of delivering mechanical inevitability can participate in symbiosis, reinforcing the balance that defines reef ecosystems. Moray eels are predominantly nocturnal hunters, emerging more fully from their crevices under cover of darkness. At night, the reef transforms. Diurnal fish retreat into hiding places, and crustaceans and cephalopods begin their own movements. The eel's reliance on olfaction becomes more pronounced in these hours. Chemical cues in the water guide it toward wounded or unsuspecting prey. The lateral line continues to detect vibrations, but scent trails often provide the initial stimulus. This combination of sensory modalities allows the eel to locate prey even when visibility declines. In low light, the second jaw becomes not merely an adaptation for confined feeding, but a guarantee that once contact occurs, the mechanics will complete the act. Thermoregulation in tropical waters may not demand the same adaptations seen in polar predators, yet temperature still influences metabolic rates and feeding frequency. Moray eels, like other ectothermic fish, rely on ambient warmth to drive enzymatic processes. Warmer water accelerates digestion, enabling more frequent feeding cycles. In cooler seasons or deeper waters, metabolic rates decline and feeding intervals lengthen. The pharyngeal mechanism ensures that each feeding event yields maximal return, compensating for periods of scarcity. From an evolutionary perspective, pharyngeal jaws are not unique to morays. Many fish possess modified gill arches that assist in processing food. What distinguishes morays is the degree of mobility and extension achieved. This specialization demonstrates how incremental changes in skeletal and muscular configuration can yield profound functional shifts. By elongating and reorienting the pharyngeal apparatus, morays transformed a passive internal structure into an active predatory tool. Such transformations underscore the plasticity of vertebrate anatomy under selective pressure. As the eel completes its swallow, the outer jaws close once more in their steady ventilatory rhythm. Only the faint ripple of muscles beneath the skin betrays the recent violence. Outside the crevice, small fish resume grazing, seemingly unaware that the rock face contains a mechanism capable of sudden, inescapable capture. The reef remains vibrant and dynamic, yet within its cavities resides a predator defined not by speed or spectacle, but by mechanical certainty. The second jaw operates beyond the visible threshold, hidden until the moment of necessity. In this layered anatomy, brutality is not explosive, but procedural, unfolding through a sequence that leaves no margin for reversal. The moray eel exemplifies how evolution can embed inevitability within structure itself, ensuring that once the initial bite is secured, the outcome is not a matter of chance but of design. The water along the outer reef slope is thick with suspended life. Currents sweep in from deeper blue, carrying drifting jellyfish, scraps of algae torn from distant beds, and the occasional carcass of something that did not survive the night. The environment feels transitional, neither fully open ocean nor sheltered lagoon, but a boundary where debris accumulates and scavengers patrol. Moving through this shifting column of organic fragments is a predator whose presence is defined not by explosive spectacle or coordinated strategy, but by relentless intake. A tiger shark glides forward with measured strokes of its crescent tail, its striped flanks fading into the green-blue haze like shadows beneath storm clouds. It does not appear hurried. Its pace suggests inevitability rather than urgency, as though it is less hunter than collector, absorbing whatever the sea relinquishes. The head is broad and blunt, giving the shark a profile that suggests force rather than finesse. Unlike more streamlined pelagic hunters that rely on speed to overtake agile prey, the tiger shark's power lies in versatility. Its jaws are framed by rows of serrated teeth, shaped not like narrow daggers, but like curved saw blades, each one deeply notched along the edge. When the mouth opens, the geometry becomes apparent. These teeth are engineered not merely to puncture, but to slice and shear. The serrations function like the teeth of a handsaw, gripping into resistant surfaces and tearing through them with rotational force. As the shark closes its jaws, muscle and cartilage apply pressure sufficient to fracture turtle shells and crush dense bone. The result is not a precise incision, but a mechanical shredding, converting armor into fragments with minimal hesitation. Ahead, a sea turtle moves slowly, its flippers pushing in deliberate strokes as it grazes along a patch of seagrass. The turtle's shell, a mosaic of keratin plates layered over bone, represents one of the ocean's most formidable defenses. For many predators, this structure is a barrier that renders the animal invulnerable. The tiger shark approaches without theatrics, its body angling slightly as it assesses the turtle's trajectory. There is no sudden sprint. Instead, it closes the distance steadily until the moment of contact arrives. The bite is decisive and anchored by those serrated edges. The shell cracks not in a single clean break, but in a spreading fracture, like ice yielding under weight. The shark does not linger to extract flesh delicately. It rotates its head side to side, enlarging the opening through torque. In a matter of seconds, the protective barrier becomes debris, and the interior tissues are exposed. What follows is consumption without selectivity. Tiger sharks are often described as indiscriminate feeders, but this characterization obscures the ecological logic behind their diet. Their stomachs have been found to contain fish, seabirds, marine mammals, turtles, and, occasionally, inanimate objects such as metal fragments or discarded human debris. The willingness to ingest a wide array of materials reflects both opportunism and physiological resilience. The shark's digestive system is lined with highly acidic gastric fluids capable of breaking down tough connective tissues and dissolving calcium-rich structures. While stomach acid in most vertebrates is potent, in tiger sharks it is paired with a robust immune system that mitigates infection risk from decaying matter. Carrion, often laden with bacteria, poses minimal threat to a predator evolved to process it regularly. The digestive tract of the tiger shark includes a spiral valve intestine, a corkscrew-shaped structure that increases surface area for nutrient absorption within a relatively short length of gut. This adaptation allows efficient extraction of calories from diverse prey types. The spiral configuration slows the passage of food, ensuring maximal breakdown and assimilation. When the shark consumes a carcass that has already begun decomposing, Microbial communities within the stomach contribute to further digestion, working alongside enzymes to reduce tissue into absorbable components. In this way, the tiger shark transforms complex biological material into usable energy, redistributing nutrients that might otherwise sink to the seafloor unprocessed. The ecological consequences of such feeding habits are profound. By consuming sick or injured animals, tiger sharks act as regulators of marine health, removing individuals that might spread disease or weaken population genetics. Their scavenging reduces the persistence of carrion, limiting bacterial blooms that could disrupt local oxygen levels. Even their ingestion of unexpected items, while sometimes harmful to the individual shark, reflects the blurred boundary between organic and anthropogenic debris in modern oceans. When metal or plastic fragments appear in their stomachs, it underscores the extent to which human materials have entered marine food webs. Yet the shark's physiology, evolved for resilience, often enables survival despite such intrusions. Beyond turtles, tiger sharks prey on seabirds that rest on the water's surface, often approaching from below with subtle adjustments in buoyancy. The oil-rich liver within their bodies provides natural lift, allowing them to hover with minimal energy expenditure. This buoyancy control is critical when targeting prey near the surface, where precision matters more than velocity. A sudden upward lunge, accompanied by a snap of serrated jaws, can capture a bird before it has time to lift into flight. The kill is not elegant. Feathers scatter across the water, and the shark resumes its steady movement, leaving only a widening ring of ripples behind. In coastal shallows, tiger sharks sometimes forage among stingrays buried in sand, using electroreception to detect faint muscle impulses beneath sediment. Their broad snouts and downward curving teeth enable them to excavate prey partially concealed in substrate. Here again, their feeding is characterized by persistence rather than speed. They root and bite, overturning sand in slow arcs until resistance yields. The resulting plumes of sediment alter microhabitats temporarily, exposing invertebrates and attracting smaller scavengers. Thus, even the act of feeding reshapes the benthic environment, creating opportunities for other species. Thermoregulation in tiger sharks is largely dependent on ambient water temperature, as they are ectothermic. However, their wide geographic distribution indicates tolerance for varied thermal conditions. Seasonal movements often align with temperature gradients and prey migrations. In warmer months, they may patrol coastal waters rich in turtles and fish, while cooler seasons draw them toward deeper offshore zones. Satellite tracking has revealed long-distance movements spanning vast oceanic regions, illustrating how digestive dominance intersects with migration patterns. The ability to consume nearly any available prey grants flexibility in these journeys, reducing dependence on a single food source. The resilience of their immune system deserves particular attention. Marine environments harbor diverse pathogens, especially in decomposing carcasses. Tiger sharks possess immune defenses that mitigate infection from ingested bacteria and parasites. Their white blood cell responses and antimicrobial peptides in mucosal tissues provide protection during digestion. This resilience is not incidental, but essential to a lifestyle that embraces carrion alongside fresh kills. The indifference to prey condition, whether alive or already decaying, reflects confidence in internal defenses. As the shark continues its patrol, fragments of consumed prey sink slowly, feeding smaller fish and invertebrates below. The cycle of transformation continues. The brutality of the tiger shark is not theatrical. There is no explosive breach or synchronized siege. Instead, there is an unwavering commitment to conversion. Shell, bone, feather, flesh, and even foreign material are reduced to biomass and redistributed through excretion and energy expenditure. The predator becomes a conduit through which matter flows, linking trophic levels in an unbroken chain. In this sense, the tiger shark functions less as a singular hunter and more as a mobile processing unit within the ocean's nutrient economy. Its serrated teeth are tools of reduction, its stomach a chamber of chemical breakdown, its immune system a shield against microbial consequence. The environment does not intimidate it with defensive shells or decaying flesh. It absorbs, dismantles, and moves on. The reef slope grows quiet once more, currents carrying away the last evidence of disruption. Yet the transformation is complete. Where there was once a turtle armored in bone, there is now energy moving through muscle and bloodstream, fueling the shark's next steady glide. The brutality here is indifference, a refusal to discriminate between prey types, a commitment to turning whatever the sea offers into continuation of its own motion. In the vast accounting of marine ecosystems, the tiger shark stands not as a specialist, but as an executor of inevitability, reducing complexity to sustenance with mechanical certainty. The continental shelf slopes gently into turquoise shallows, where sunlight penetrates all the way to the sand, illuminating a mosaic of ripples sculpted by tide and wind. Here, visibility can stretch for dozens of meters, and yet concealment remains surprisingly effective. Beneath a thin veil of sand lie stingrays, flattened bodies pressed flush against the seabed, gill slits fluttering as they draw water across their respiratory surfaces. Their dorsal surfaces mirror the color of sediment, and their outlines dissolve into the shifting geometry of light and shadow. From above, the seabed appears undisturbed, a calm expanse broken only by the occasional darting fish. It is an illusion sustained by camouflage and stillness, and for many predators, it works. Across this open plain moves a silhouette unlike any other in the ocean. The hammerhead shark glides in slow, deliberate arcs, its body elegant and streamlined, but its head expanded outward into a broad horizontal structure known as the cephalofoil. From above, the shape is unmistakable, resembling a wing more than a snout. At each end of this living hammer, eyes project laterally, granting a panoramic field of vision that spans nearly the entire horizon. Between these eyes and along the underside of the cephalofoil are thousands of microscopic sensory pores, known as ampullae of Lorenzini. These jelly-filled canals connect to specialized receptors capable of detecting faint electrical fields generated by muscle contractions in nearby organisms. The hammerhead's movement across the sand is methodical rather than hurried. It sweeps its head side to side in gentle oscillations, not unlike a prospector scanning ground with a metal detector. The analogy is not poetic but functional. Each sweep expands the shark's sensory reach, increasing the surface area over which electrical signals can be sampled. In most sharks, the electroreceptive organs are concentrated near the snout, forming a localized cluster. In hammerheads, the lateral expansion of the cephalofoil distributes these receptors across a wide span, enhancing spatial resolution. The shark does not simply detect that something is alive beneath the sand, it can triangulate its position with remarkable accuracy. The stingray beneath the sediment remains motionless, trusting its camouflage and flattened profile. Its pectoral fins are buried, and only subtle undulations betray the act of respiration. Yet even this faint muscular activity produces bioelectric fields. Every nerve impulse and contraction emits a trace electrical signal into the surrounding water. The conductivity of seawater allows these signals to propagate outward, and the hammerhead's sensory array intercepts them. As the shark passes overhead, the cephalofoil tilts slightly, fine-tuning the reception of gradients between left and right sides. The difference in signal strength guides the predator to adjust its path, narrowing in on the concealed prey with incremental precision. The cephalofoil serves multiple purposes beyond electroreception. Its expanded surface generates lift as the shark swims, functioning somewhat like a hydrofoil. This lift allows the shark to maintain stable positioning close to the seafloor with reduced energy expenditure. In shallow hunting grounds, such stability is critical. The shark must hover low enough for accurate detection, but remain agile enough to react instantly when contact is made. The head's broad shape also enhances maneuverability, acting as a rudder during tight turns. These hydrodynamic advantages converge during the final moments of the hunt. When the hammerhead detects a stingray directly beneath it, the shift from scanning to action is abrupt but controlled. The shark angles downward, accelerating just enough to close the gap. In a fluid motion, it presses the flat surface of its head against the sand, pinning the ray in place. This maneuver is more than brute force. It is an exploitation of geometry. The stingray's body, adapted for life pressed against sediment, cannot easily twist free once immobilized from above. The hammerhead's cephalofoil effectively functions as a clamp, preventing the ray from flapping upward or burying itself deeper. The stingray's primary defense lies in its venomous barb, positioned along the tail. In many predator-prey interactions, this spine deters attack. However, the hammerhead's strategy neutralizes the threat. By pinning the ray at the head and body, the shark restricts tail movement and angles its own jaws to avoid the barb. It then delivers a series of disabling bites to the ray's wings and central disc, targeting muscle and cartilage. The serrated teeth of the hammerhead slice through tissue with measured efficiency, severing locomotor capacity before consuming the prey. The sequence is not chaotic. It is surgical. The brutality in this interaction stems from precision rather than spectacle. The stingray never had the opportunity to flee because it was located before it was visible. Its camouflage, effective against vision-based predators, is rendered irrelevant by electroreception. The hammerhead transforms the ocean floor into a readable map of electrical signatures, detecting life hidden beneath layers of sand. In this realm, invisibility through coloration is insufficient. The predator hunts by physiology rather than by sight alone. The sensory superiority of hammerheads extends beyond electroreception. Their wide-set eyes grant binocular overlap in unexpected ways. While positioned laterally, the eyes can tilt and rotate, allowing overlapping fields of vision beneath the head. This capability enhances depth perception during close-range strikes. Additionally, their olfactory organs are highly developed, detecting dissolved chemicals in the water that signal the presence of injured prey or reproductive cues. Together, these sensory modalities create a composite awareness that integrates sight, smell, vibration, and electricity into a unified hunting strategy. Hammerheads often patrol in groups during certain times of year, particularly around seamounts and offshore reefs. These aggregations may number in the hundreds, forming schools that move in coordinated formations. While the precise function of such gatherings remains a subject of study, hypotheses include social interaction, reproductive behavior, and navigation. During solitary hunting on sandy flats, however, the individual operates independently. The group dynamic dissolves into personal precision, and each shark becomes a self-contained detection system scanning the seabed. Thermoregulation in hammerheads, as in most sharks, relies on ambient conditions, yet some species exhibit partial endothermy, maintaining slightly elevated muscle temperatures that enhance performance. In warm coastal waters, where stingrays thrive, metabolic rates support sustained foraging across broad areas. Seasonal migrations may carry hammerheads along continental margins, following prey abundance and reproductive cycles. The availability of shallow sandy habitats influences distribution patterns, and areas with rich benthic communities become reliable hunting grounds. The ecological implications of this predation are significant. Stingrays consume mollusks and crustaceans, influencing benthic invertebrate populations. By regulating ray numbers, hammerheads indirectly affect the composition of seafloor communities. In regions where hammerhead populations decline due to fishing pressure, shifts in ray abundance can cascade through ecosystems, altering sediment dynamics and prey availability for other species. The electrohunter thus occupies a pivotal role in maintaining balance along the continental shelf. As the hammerhead completes its meal, fragments drift downward and smaller fish gather to scavenge. The sand, briefly disturbed by the struggle, resettles in soft ripples. The shark resumes its scanning glide, cephalofoils sweeping rhythmically, receptors attuned to faint currents of electricity. The seabed stretches ahead like an unwritten script, each concealed organism broadcasting involuntary signals into the conductive medium. For the hammerhead, the ocean floor is never truly silent. It hums with the bioelectric signatures of hidden life. In this quiet precision lies the essence of its brutality. There is no explosive breach, no prolonged chase, no dramatic siege. Instead, there is detection before revelation, immobilization before escape. The hammerhead does not rely on prey making a mistake. It uncovers prey that believed itself invisible. Its advantage is embedded in anatomy, in the expanded architecture of a head shaped by millions of years of selective pressure favoring enhanced sensory resolution. In the interplay between camouflage and detection, the hammerhead stands as a testament to the power of perception. It hunts not merely with teeth, but with awareness, converting faint electrical whispers into decisive action, and transforming hidden refuge into exposed vulnerability with the sweep of a living instrument. In the warm, shallow flats where sunlight filters through a wavering surface and settles in rippling patterns across pale sand, the ocean appears exposed and honest. Small waves comb the shoreline in slow repetition, and the seabed seems empty except for scattered shells and faint tracks left by crabs during the night. Yet beneath this surface, simplicity lies a strategy built on concealment so complete that even trained eyes struggle to detect it. A stingray rests motionless against the sand, its flattened body pressed flush to the substrate, edges barely distinguishable from the surrounding sediment. Only the faint spirals of water drawn through its spiracles hint at life beneath the sand. Its coloration mirrors the bottom precisely, mottled in muted browns and greys that dissolve into the light's distortion. The stingray is not an aggressor in this landscape. It does not pursue prey through open water with overt force. Instead, it buries itself partially beneath the sand, leaving only eyes and breathing openings exposed. From this vantage point, it waits for small crustaceans or mollusks to wander close. Its pectoral fins undulate in slow, wave-like motions, stirring sediment just enough to expose hidden invertebrates. When prey is located, the ray lifts gently and settles forward, pinning the organism beneath its disc before crushing it with specialized dental plates. The feeding is deliberate and efficient, driven by a body design optimized for bottom dwelling rather than pursuit. Yet behind this calm posture lies an adaptation that transforms defense into lethal potential. Along the tail, near its base, a rigid spine extends backward, often concealed in the sand when the ray rests. This spine, composed of dentin and serrated along its edges, is more than a structural appendage. It is connected to venom glands embedded within grooves that run along its length. When the stingray feels threatened, muscles at the tail's base contract with sudden intensity, arching the tail upward and forward in a swift whipping motion. The spine, previously unnoticed, becomes a concealed dagger propelled toward whatever has crossed the boundary of safety. This defensive strike is reactive, not predatory. The stingray does not stalk with its spine raised. Instead, it deploys the weapon when startled or cornered. In shallow waters, this often occurs when a larger animal or human inadvertently steps upon or near it. The whipping motion is rapid, driven by powerful musculature at the tail base that converts stored tension into forward thrust. The serrations along the spine's edges ensure that once it penetrates tissue, withdrawal can cause additional tearing. Simultaneously, venom from the glandular grooves is delivered into the wound. The venom itself is a complex cocktail of proteins and enzymes that induce intense localized pain, inflammation, and tissue necrosis. The pain can be immediate and overwhelming, radiating outward from the puncture site as nerve endings respond to chemical assault. The purpose of this venom is not to paralyze prey, but to deter predators. In evolutionary terms, inflicting severe pain increases the likelihood that a predator will release the stingray and avoid future contact. The brutality lies in its suddenness and in the severity of its response. What begins as an accidental intrusion becomes a violent exchange in which the stingray's survival hinges on inflicting maximum deterrence in a single motion. On the flats, larger sharks occasionally prey upon stingrays, employing strategies to avoid the barb. Some species flip rays onto their backs, immobilizing the tail before biting into the softer underside. This interaction underscores the dynamic nature of predator-prey evolution. The stingray's spine is effective, but not invincible. Predators adapt to neutralize it, just as rays refine their camouflage and reflexes. The ecosystem becomes a dialogue of adaptations, each species adjusting to the other's innovations. The stingray's physiology is intricately tuned to its benthic lifestyle. Its flattened body increases surface area, distributing weight evenly and allowing it to glide over sediment with minimal disturbance. The spiracles positioned atop its head enable respiration while the mouth remains buried beneath sand. Electroreceptors embedded in the skin detect faint electrical signals from prey concealed below, guiding feeding movements even when visibility is reduced. These sensory adaptations allow the stingray to function as both predator and prey within the same ecological niche. Thermoregulation in shallow coastal waters requires resilience to fluctuating temperatures. Tidal cycles expose rays to varying thermal gradients, and some species migrate seasonally along coastlines to remain within optimal ranges. In colder months, rays may move into deeper channels where temperatures are more stable. In warmer seasons, they return to flats rich in invertebrate prey. This migration is not dramatic in distance compared to pelagic species, but it reflects a sensitivity to environmental cues that shape distribution patterns. Reproduction adds another layer to their ecological role. Many stingrays are ovoviviparous, meaning embryos develop within the mother's body, nourished initially by yolk and later by uterine secretions. The young are born fully formed, miniature versions of adults, already equipped with a small but functional spine. This early acquisition of defensive capability reflects the necessity of deterrence in open shallows where predation risk is constant. From birth, the stingray carries its concealed dagger, a reminder that vulnerability and defense coexist within the same anatomy. Human encounters with stingrays often highlight the reactive nature of their brutality. Incidents typically occur when an individual inadvertently steps on a buried ray. The reflexive strike is not an act of pursuit, but of startled defense. Education efforts in coastal communities emphasize shuffling feet while wading, creating vibrations that alert rays to human presence and reduce surprise. This behavioral adaptation illustrates how knowledge of ecological mechanics can mitigate conflict between species. Within the broader ecosystem, stingrays influence sediment dynamics through their feeding behavior. As they disturb sand while searching for invertebrates, they aerate the substrate, affecting nutrient exchange and microhabitat structure. Their presence can alter the distribution of benthic organisms, shaping community composition subtly over time. Thus, even as defensive specialists, they contribute to ecological processes beyond immediate interactions. As evening light deepens and shadows lengthen across the flats, the stingray resumes its near-invisible posture. The spine lies hidden once more, tail resting gently against the sand. Small fish drift overhead, unaware of the weapon concealed below. The water's surface reflects hues of gold and blue, and the scene returns to tranquility. Yet beneath that calm lies readiness, a system designed to convert vulnerability into devastating reaction in a fraction of a second. The stingray's brutality is neither premeditated nor flamboyant. It is the consequence of being both hunter and hunted in a landscape without shelter. Its venomous barb embodies a principle of survival through deterrence, ensuring that even a creature defined by camouflage can command respect. In the silent tension between concealment and intrusion, the stingray stands as a testament to reactive power, a guardian of its own fragile territory, armed with a hidden blade that transforms accident into unforgettable consequence. The sea at high latitudes in feeding season feels alive in a way that is difficult to describe from shore. Cold air presses low over the water, and each wave carries a metallic sheen under a pale sun. Beneath the surface, the ocean is thick with motion, layered with currents that transport plankton blooms and the small fish that follow them. Herring, sand lance, and other schooling species gather in immense numbers, drawn to the seasonal abundance that erupts when daylight returns and phytoplankton multiply. The fish move as a single shimmering body, a living cloud that stretches across the water column, pulsing and compressing as if it were breathing. In this crowded arena, predators arrive not simply to chase, but to engineer. A humpback whale rises from the dim green depths with slow certainty, its massive body moving like a submarine carved from muscle and blubber. The whale is not a creature of constant pursuit. It is built for long migrations between warm breeding grounds and cold feeding seas, conserving energy across thousands of miles by gliding and timing its exertion. Its body is insulated by thick blubber, and beneath that layer, oxygen is stored in blood and muscle in concentrations that allow extended dives. The flippers, long and scalloped with knobby tubercles, pivot gently as the whale adjusts its position. These tubercles are not random texture, but hydrodynamic tools, reducing drag and delaying stall during tight maneuvers, allowing a creature of immense size to turn with surprising precision. In a world where most large animals rely on brute momentum, the humpback displays something closer to agile intention. The whale is not alone. In many feeding grounds, humpbacks hunt cooperatively, forming temporary teams that coordinate their movements. Their communication is subtle and largely invisible to surface observers. Low-frequency vocalizations and pulses travel through the water, not as the elaborate songs used in breeding displays, but as functional signals that align timing and position. The whales may circle beneath a school of fish, each individual adjusting depth and trajectory based on cues from the others. Their collective goal is not simply to bite into the school, but to compress it, transforming a diffuse swarm into a dense, harvestable mass. The brutality here is not in tooth or claw, but in environmental manipulation. They reshape the water column itself into a trap. The bubble net begins with motion and breath. One or more whales dive beneath the fish and begin swimming in a widening spiral. As they move, they release streams of bubbles from their blowholes, producing a rising curtain of shimmering spheres that expands upward and outward. These bubbles are more than visual distraction. They create a physical and sensory barrier. Fish interpret bubbles as turbulence, a zone of danger, and they instinctively avoid passing through it. The rising wall thus functions like a fence in 3 dimensions, a living boundary that grows as the whales circle. In a matter of seconds, the spiral tightens, and the fish are herded toward the center. Their schooling instincts, which normally provide protection through collective confusion, now work against them. Each fish responds to the movement of its neighbors by tightening formation, compressing into a dense ball. This is why bubble net feeding can be compared to underwater farming. The whales do not merely hunt, they cultivate a harvest by shaping prey distribution. They locate a resource patch, surround it, and then manipulate the environment to concentrate that resource into a usable form. The spiral bubble wall is like an engineered enclosure built from breath. In terrestrial farming, fences and corrals restrict movement. Here, bubbles do the same, exploiting prey behavior and physics simultaneously. The whales harvest without chasing individuals across distance. Instead, they convert the ocean's open space into a temporary structure with boundaries that prey perceive as impassable. Within the spiral, the fish attempt to escape upward, but the bubble wall rises with them. Some whales contribute additional tactics, such as producing loud vocalizations sometimes described as feeding calls. These sounds may further disorient prey or encourage tighter clustering, though the exact mechanisms remain an active area of study. What is clear is that humpbacks display behavioral flexibility, adjusting bubble net geometry depending on prey type, current strength, and team size. In some cases, one whale acts as a bubble blower, while another positions beneath the school to deliver the final strike. Roles may rotate, suggesting not only cooperation, but division of labor. Such complexity indicates learned behavior passed culturally between individuals and generations. At the climax of the trap, the whales surge upward through the center of the bubble net with mouths open wide. The gape is enormous, and pleated throat grooves expand like accordion folds, allowing the whale to engulf a volume of water and prey that seems impossible for its body size. This is lunge feeding, a strategy that relies on momentum and expandable anatomy. The whale accelerates upward, using stored muscular power to breach the prey ball. Water and fish rush into its mouth, and the throat expands dramatically, ballooning with intake. Then, as the jaws close, the whale filters water out through baleen plates that hang like combs from the upper jaw. These plates trap fish while water is expelled. The fish, once free in open ocean, are now pressed against keratinous fringes, funneled toward the throat and swallowed. The brutality of this feeding is not messy in the way of tearing predators, yet it is profoundly decisive. Thousands of fish can vanish in a single engulfment. The prey does not die in individual combat. It is harvested as a collective. The whale does not need to identify a single target. It targets the school itself as an entity, capturing its density and transforming it into nutrition. This is why bubble net feeding is an ecological force beyond the immediate kill. It alters fish survival not by selective predation, but by mass removal events, which can influence local prey population dynamics and distribution. The ecological relationships surrounding bubble net feeding extend further. Seabirds often gather overhead when whales begin feeding, drawn by fish pushed toward the surface. Gulls and shearwaters dive into the chaos, exploiting prey that scatter or become trapped near the bubble wall. Other marine predators, such as dolphins or seals, may join opportunistically, hunting fish fleeing the net's edges. The whales, therefore, act as ecosystem engineers during feeding events, creating localized resource pulses that attract a community of scavengers and secondary predators. This phenomenon demonstrates how apex predators can shape not only prey populations, but also the behavior and success of other species in the same habitat. Thermoregulation and migration underpin the whale's ability to participate in this feeding strategy. Humpbacks spend much of the year in warm waters where they breed and calve, often fasting or feeding minimally. Their return to cold feeding grounds is driven by the need to rebuild energy reserves. The blubber layer thickens during feeding season, storing calories for future migration and reproduction. This seasonal feast and famine cycle imposes strong selective pressure for efficient feeding strategies. Bubble netting is one of the most efficient methods available to a baleen whale because it maximizes prey capture relative to energy expended. A coordinated net reduces wasted chases and increases predictability of intake, crucial when limited time exists to accumulate reserves. The cognitive demands of bubble net feeding are significant. It requires spatial awareness, timing, and the ability to anticipate prey behavior. Each whale must adjust its bubble release rate, swimming speed, and spiral radius in response to current and prey movement. Misalignment could allow fish to escape, wasting effort. That the whales execute this repeatedly suggests not only individual learning, but social transmission. Calves observe feeding behavior alongside adults, gradually learning the patterns of movement and timing needed to build a net. In this way, feeding strategy becomes culture, embedded in group identity and passed down through years. Even within the same species, different populations may use different feeding techniques. Some humpbacks rely on solo lunge feeding without bubble nets, while others specialize in complex nets requiring multiple individuals. This variation reflects adaptability to local prey ecology and environmental conditions. Where schooling fish are abundant and predictable, bubble netting thrives. Where prey is dispersed or different in behavior, other strategies dominate. This underscores the idea that intelligence in whales is not a generalized trait, but expressed through context-specific solutions shaped by ecological necessity. As the feeding event concludes, the bubble curtain dissipates, rising and bursting at the surface, leaving only faint turbulence behind. The fish school, diminished and scattered, reforms at a distance, its shimmering unity disrupted. The whales descend again into darker water, their massive bodies fading into green depths as they prepare for another engineered harvest. Above, birds continue circling, and the surface returns to its cold calm. Yet the water column has been reshaped, temporarily structured by breath and intention. The humpback whale's bubble net feeding embodies brutality through environmental manipulation. It is not the violence of a single predator overpowering a victim, but the violence of turning open water into a trap. It is the ability to transform prey abundance into inevitability by re-engineering space. In the cold seas of the feeding grounds, where survival depends on extracting massive energy from fleeting abundance, the humpback's intelligence becomes physical. It builds fences from bubbles, farms the water column, and harvests life in dense, sudden gulps. In this process, the ocean itself becomes part of the predator's anatomy, shaped and exploited in a way that reveals the profound power of coordinated behavior at immense scale. The reef at first appears intact, a mosaic of coral heads rising from pale sand, punctuated by sponges and sea fans that sway in the current. Small damselfish hover in territorial clusters, parrotfish grind algae from limestone, and cleaner wrasses dart between larger bodies in brief exchanges of mutual benefit. The system is layered and intricate, built on countless interactions that have stabilized over generations. Yet within this living architecture, a new silhouette drifts with deliberate composure. Its fins do not fold tightly to its body like most predatory fish. Instead, they flare outward in broad, ornate fans, striped in alternating bands of rust, white, and dark brown. The lionfish moves slowly, almost lazily, its dorsal spines erect like a crown of needles that shimmer under filtered sunlight. It does not chase frantically or accelerate in bursts. Its brutality is patient and geometric. The dorsal spines are not mere ornamentation. Each spine is connected to venom glands that secrete a complex mixture of proteins capable of inducing intense pain, tissue swelling, and in some cases systemic shock in would-be predators. The venom does not function as an offensive toxin in feeding, but as a defensive deterrent, ensuring that few natural predators attempt to swallow or bite the lionfish without consequence. This chemical shield grants the fish unusual freedom in its movement. It can approach prey with little concern for ambush from behind. The spines, when extended, create a perimeter that radiates warning. In their native Indo-Pacific waters, potential predators have learned through painful encounters to respect this perimeter. In regions where the lionfish has become invasive, such as parts of the Atlantic and Caribbean, local predators lack this evolutionary history. The result is a predator moving through unfamiliar ecosystems with minimal restraint. The lionfish's hunting strategy relies less on speed than on manipulation of space. As it nears a cluster of small reef fish, it extends its large pectoral fins outward and forward, creating a semicircular barrier. These fins, translucent and banded, resemble the slats of a fence that slowly narrows. The prey, sensing motion but unable to interpret its intent fully, respond by tightening their formation. In doing so, they move precisely where the lionfish intends. The predator advances incrementally, reducing the available escape corridor. Unlike swift hunters that strike from distance, the lionfish closes space until its mouth is within a few centimeters of a target. In a rapid suction event, it expands its buccal cavity and engulfs the prey whole. The act is so quick that it often appears as though the fish has simply vanished into the predator's mouth. This behavior is not accidental but supported by anatomical specialization. The lionfish's jaws are capable of remarkable expansion, allowing it to generate a focused suction force that draws in small fish with minimal pursuit. The extended fins serve both as visual camouflage and as a corral. By spreading them, the lionfish appears larger and more complex, confusing prey that rely on visual cues to identify threats. In some observations, lionfish have been seen using water jets to disorient prey before striking, directing bursts of water from their mouths to disrupt schooling cohesion. Such behavior underscores a level of behavioral flexibility that enhances their efficiency. The chemical warfare implied by venomous spines extends beyond individual defense. The presence of lionfish in non-native reefs has measurable ecological consequences. Small herbivorous fish that graze on algae are often among the first to decline in areas with established lionfish populations. Without these grazers, algae can overgrow coral, smothering polyps and reducing reef resilience. In this way, the lionfish's predation cascades through trophic levels, altering community composition and ecosystem function. The brutality becomes systemic rather than immediate. Reef fish populations may decline by significant percentages within a few years of lionfish establishment, and recovery can be slow or incomplete. The success of lionfish in invaded habitats is tied to their reproductive strategy. Females can release egg masses frequently throughout the year, each mass containing thousands of eggs encased in gelatinous matrices that drift with currents. Fertilization occurs externally, and larvae disperse widely before settling onto suitable reef substrates. This high fecundity, combined with the absence of specialized predators in new regions, accelerates population growth. Juvenile lionfish quickly adopt the same defensive posture as adults, spines erect and fins extended, reinforcing survival at every stage. Thermoregulation in lionfish is consistent with tropical reef species, yet their tolerance for varied salinity and temperature conditions contributes to their invasive success. They have been recorded in depths ranging from shallow reefs to mesophotic zones far below typical snorkeling depths. This vertical flexibility allows them to exploit prey communities that other predators might not access. In deeper waters, where fishing pressure is reduced, lionfish populations can flourish undetected, serving as reservoirs that replenish shallower reefs. Predator-prey interactions involving lionfish are marked by asymmetry. In their native range, groupers and other large predatory fish occasionally consume lionfish, suggesting that evolutionary familiarity mitigates venom risk. In invaded ecosystems, however, predation rates are minimal. Efforts to train native predators to recognize lionfish as prey have met with limited success, illustrating the complexity of learned behavior in marine systems. Human intervention, through targeted removal and culling, has become a primary control method in some regions. Divers spear lionfish to reduce their density, and the species has even entered culinary markets as a means of population management. Yet the scale of invasion often exceeds localized removal efforts. The slow, methodical advance of a lionfish across a reef resembles a creeping fence line that shifts incrementally but inexorably. Prey species that once relied on quick dashes between coral branches find themselves funneled into narrowing spaces. The predator does not need to outrun them, it only needs to outmaneuver them. Each feeding event removes another individual from the community, and over time, the cumulative effect becomes visible. Juvenile fish cohorts shrink, biodiversity declines, and the intricate choreography of reef interactions begins to falter. The venomous spines serve as both shield and symbol. They project outward, warning of chemical defense that deters interference. For humans, envenomation can result in intense pain and swelling, though fatalities are rare. For reef predators unfamiliar with the toxin, a single encounter may be enough to establish avoidance behavior. The lionfish thus moves with a confidence derived from chemistry, insulated by proteins that discourage confrontation. As currents shift and the sun lowers toward the horizon, the reef takes on a golden hue. The lionfish hovers among branching corals, fins extended, dorsal spines casting slender shadows on the substrate. Around it, smaller fish maintain cautious distance. The ecosystem continues to function, yet the balance is altered subtly with each passing day. The brutality here is not explosive, but cumulative. It is the steady erosion of diversity through relentless, efficient predation. It is the transformation of vibrant reef communities into simplified assemblages dominated by a predator few can challenge. In this unfolding narrative, chemical warfare and spatial manipulation converge. The lionfish does not dominate through speed or spectacle, but through geometry and toxin, turning reef corridors into controlled funnels and projecting a barrier that few dare cross. The slow ecological strangulation that follows is a reminder that not all devastation announces itself with noise. Sometimes it advances on delicate fins, crowned with venom, reshaping ecosystems one silent engulfment at a time. The Arctic shoreline in late summer appears deceptively calm. Sheets of sea ice drift beyond the horizon, fractured into pale platforms that grind softly against one another with the rhythm of distant thunder. Along the gravel beaches and muddy shallows, massive brown bodies cluster in dense aggregations, their weight pressing into the earth as though the land itself must brace against them. Steam rises from their hides in the cold air, mingling with the briny scent of tidal flats exposed by a retreating sea. These are walruses, animals whose presence is defined not by speed or agility, but by gravity and force. Each individual carries layers of blubber that insulate against Arctic waters, yet beneath that insulating mass lies a muscular frame capable of surprising dexterity. At first glance, they appear almost cumbersome, their whiskered faces and elongated tusks lending them a strange combination of solemnity and menace. In truth, their brutality unfolds in a manner that is less theatrical than relentless, a quiet dominance expressed through mass and mechanical efficiency. A mature male walrus can weigh as much as a small vehicle, and when he shifts his position on the beach, the ground trembles faintly. The tusks that project downward from his upper jaw are elongated canines growing continuously throughout his life. They are not merely ornaments or relics of ancestry, but functional tools shaped by evolutionary pressure. During the breeding season, when females haul out onto ice floes to rest and nurse calves, males compete for proximity and access. These confrontations rarely begin with immediate violence. Instead, they escalate through displays of posture and sound. Deep bellows reverberate across the water, signaling size and strength. When two males close the distance, tusks become instruments of leverage. They press against one another, testing resolve, pushing and twisting in contests that measure endurance and power. If the display fails to resolve tension, tusks can become weapons. A downward thrust delivered with the force of a massive body can puncture thick skin and leave deep scars. Such injuries are not superficial. They may penetrate blubber and muscle, causing bleeding that stains the pale ice crimson before freezing into dark patches. Yet even in these moments of violence, there is calculation. The walrus does not lunge with reckless abandon. Its thick hide and blubber layer provide some protection against counterstrikes, but a misplaced thrust could cause severe injury. The confrontation is therefore a balance between intimidation and measured force, where dominance is established through the capacity to wound without self-destruction. The same tusks serve purposes beyond rivalry. In icy waters, walruses use them to haul their enormous bodies onto floating platforms, embedding the tips into ice and levering upward with the strength of neck and shoulder muscles. This behavior conserves energy in an environment where repeated swimming to shore would expend precious reserves. In this sense, tusks represent multifunctional tools that integrate social hierarchy, locomotion, and defense into a single anatomical feature. Their continued growth throughout life ensures that older males possess longer, more imposing weapons, reinforcing social structure through visible markers of age and survival. Yet the most distinctive aspect of walrus brutality is neither dueling nor hauling, but feeding. Beneath the surface of Arctic shallows lies a vast expanse of benthic invertebrates, particularly clams, buried within sediment. The walrus descends into these cold waters with a controlled grace that belies its bulk. Its whiskers, known as vibrissae, form a dense array of tactile sensors around the muzzle. Each whisker connects to a rich network of nerves capable of detecting minute differences in texture and movement along the sea floor. As the walrus glides over the sediment, it lowers its face and sweeps these vibrissae across the bottom, probing for the subtle protrusions that signal buried prey. Once a clam is located, the walrus does not rely on crushing jaws to break it open. Instead, it employs a feeding mechanism based on suction. The tongue, muscular and highly flexible, retracts rapidly within the oral cavity, creating a negative pressure zone. This sudden drop in pressure functions like an industrial extraction pump, drawing the soft body of the clam out of its shell while leaving the hardened exterior behind. Observations of feeding grounds reveal scattered shells with little internal tissue remaining, evidence of this efficient extraction process. The suction force generated can be substantial, capable of dislodging prey embedded several centimeters beneath sediment. By relying on suction rather than shell crushing, the walrus minimizes wear on its teeth and conserves energy. The physiology underlying this suction feeding is intricate. The walrus's lips form a tight seal around the prey site, preventing water from diluting the negative pressure. Muscles surrounding the pharynx and oral cavity coordinate in rapid contraction, amplifying the vacuum effect. This adaptation allows the walrus to consume thousands of clams in a single feeding session, converting benthic biomass into caloric reserves essential for survival in frigid climates. The efficiency of this method underscores the relationship between anatomical specialization and ecological niche. In an environment where prey is abundant but encased in hard shells, suction offers a solution that bypasses structural defenses. Thermoregulation in walruses depends on both blubber insulation and vascular adjustments. When submerged in icy water, peripheral blood vessels constrict to reduce heat loss, directing circulation toward vital organs. Upon hauling out, blood flow increases to the skin, releasing excess heat. This vascular control allows walruses to maintain core temperature despite prolonged exposure to sub-zero conditions. Their large body size contributes to thermal inertia, reducing the rate at which internal temperature fluctuates. In this context, mass becomes an ally not only in dominance displays, but in survival itself. The ecological impact of walrus feeding extends beyond individual consumption. By disturbing sediment while foraging, walruses aerate the seafloor, influencing nutrient cycling and altering microhabitats. The shells left behind accumulate in patches, providing substrate for smaller organisms and shaping benthic community structure. In areas with dense walrus populations, this constant reworking of sediment can transform entire sections of coastal seabed, redistributing organic matter and affecting species composition. Thus, their suction feeding is not a minor detail, but a process with ecosystem-level consequences. Calves remain close to their mothers during early life, learning feeding grounds and migration routes through observation and proximity. Migration patterns often follow the advance and retreat of sea ice, aligning with seasonal prey availability. As ice coverage changes due to shifting climate conditions, walruses adjust haul-out behavior, sometimes congregating on land in unprecedented numbers. Such gatherings increase the risk of trampling, especially among younger individuals, highlighting the delicate balance between mass and vulnerability. The same weight that grants dominance can become a liability in crowded conditions. Predation on walruses by apex predators such as polar bears is rare and typically limited to calves or weakened individuals. The adult walrus's size and tusks provide formidable defense. When threatened in water, a group may form a defensive cluster, tusks oriented outward. In this configuration, the blunt force dominance of sheer mass combines with pointed weaponry to deter attack. The strategy mirrors their approach to rivalry. Present the force first, escalate only if necessary. As dusk settles over the Arctic shore, the colony grows quieter. Some individuals slip back into the water, their immense bodies disappearing beneath the surface with barely a splash. Beneath the waves, they resume their methodical search across the seafloor, whiskers grazing sediment, tongues poised to create vacuum pulses that draw hidden life into their mouths. There is no dramatic pursuit, no sudden strike that splits water into foam. Instead, the brutality of the walrus unfolds in slow, crushing inevitability. Tusks test rivals and repel threats, while suction extracts sustenance from beneath hardened shells. Strength manifests not in speed, but in the capacity to move immense weight and to manipulate pressure with precision. In this frozen frontier, survival belongs to those who convert mass into advantage. The walrus embodies that principle with understated authority. Its dominance is not flashy or explosive, but persistent, expressed through mechanical leverage and physiological adaptation. Each feeding dive reshapes the seafloor, each tusk clash reinforces hierarchy, and each haul onto ice confirms mastery over a landscape defined by cold and scarcity. The Arctic does not reward delicacy. It rewards those who can endure and exert force without hesitation. In the walrus, crushing strength and vacuum precision converge, revealing a form of brutality that is steady, deliberate, and profoundly effective. Along the cold, rock-strewn seabed of the North Atlantic, where kelp forests sway in the steady pulse of tidal currents, life moves with deliberate caution. Boulders lie draped in encrusting algae, and crevices shelter brittle stars, crabs and mollusks that feed in the dim, filtered light. The water carries a metallic chill even in summer, a reminder that these latitudes favor endurance over haste. Beneath a ledge shadowed by waving fronds of kelp, a lobster waits with patient stillness. Its body is armored in a rigid exoskeleton, mottled in hues of dark green and brown that blend seamlessly with rock and seaweed. Long antennae extend outward, tracing arcs through the water, sampling chemical cues carried by the current. It appears almost ancient, a creature assembled from plates and joints rather than flesh. Yet within that shell lies a system of pressure and leverage refined through incremental growth across decades. The lobster's most conspicuous features are its claws, asymmetrical instruments that serve distinct functions. One claw, often slightly smaller and more agile, is the cutter, lined with sharp edges capable of slicing softer prey. The other, bulkier and more robust, is the crusher. This is not a decorative variation, but a biomechanical specialization. The crusher claw is packed with enlarged muscle fibers arranged to maximize force rather than speed. When the lobster flexes this claw, the closing motion concentrates power onto a small surface area. The exoskeleton at the claw's tip is reinforced, thicken to withstand immense stress without fracturing. In this design, force multiplies as it would in a hydraulic press, converting muscular contraction into crushing pressure sufficient to shatter the shells of clams, snails, and even other crustaceans. The seabed around the lobster bears evidence of this capacity. Scattered fragments of broken shell lie among stones, the remnants of encounters that ended in irreversible compression. A mussel, anchored to rock by fibrous threads, seems secure against most threats. Its shell is hinged tightly, and the adductor muscle within clamps it shut with surprising strength. Yet when the lobster approaches, guided by chemical signals released by the mollusk's filtration activity, the outcome is determined by mechanics rather than contest. The lobster positions the crusher claw carefully, aligning the shell within the curvature of its grip. With a slow, deliberate squeeze, pressure builds. The mussel resists briefly, but the structural limits of calcium carbonate are finite. A sharp crack resonates faintly through the water as the shell yields, collapsing under force. The lobster then employs its cutter claw and mouthparts to extract the soft tissue within, converting armored biomass into nourishment. This process is not hurried. Lobsters are not creatures of rapid pursuit, but of calculated application of strength. Their feeding reflects an energy strategy suited to cold waters, where metabolic rates are lower and growth unfolds gradually. Thermoregulation in lobsters is passive. As ectotherms, their body temperature mirrors that of the surrounding sea. In colder environments, metabolism slows, extending lifespan and reducing the frequency of molting. This slow pace contributes to a remarkable longevity. Some lobsters may live for decades, continuing to grow incrementally as long as they molt successfully. Each molt allows the animal to shed its restrictive exoskeleton and expand into a slightly larger form. With each cycle, muscle mass can increase, and the crusher claw, in particular, can become more formidable. Molting itself is a vulnerable interval. As the lobster prepares to shed its shell, it reabsorbs calcium to conserve resources, softening the exoskeleton from within. The old shell splits, and the lobster wriggles free, emerging temporarily pliable and defenseless. During this phase, it retreats deep into crevices, avoiding predators that might exploit its softness. Once the new exoskeleton hardens, mineralization restores rigidity, and the cycle of incremental empowerment resumes. Over years, the crusher claw thickens and strengthens, the muscles within expanding with each molt. Age becomes an asset. Where many predators peak early in life, the lobster's lethality increases as it grows. The structural composition of the crusher claw merits closer examination. The interior is packed with slow-twitch muscle fibers capable of sustained force. The lever system created by the joint amplifies that force at the tip, focusing pressure onto prey. Measurements of claw strength in large individuals reveal crushing forces comparable to industrial compression devices, sufficient to break shells that would resist most other benthic predators. Yet this power is deployed with precision. The lobster does not crush indiscriminately, but positions prey carefully, ensuring maximal efficiency with minimal energy expenditure. Social interactions among lobsters also revolve around claw mechanics. When two individuals contest a shelter, they raise their claws in displays that signal size and strength. Often, these confrontations resolve without contact, the larger crusher claw deterring challenge through sheer visual assertion. If contact occurs, claws interlock in tests of leverage. Injuries can result, including loss of limbs. However, lobsters possess the ability to regenerate lost claws over subsequent molts, a capacity that underscores the resilience embedded in their life history. A lost crusher claw may regrow initially as a cutter, but through repeated molts and shifts in use, asymmetry can re-establish itself. The flexibility of this system ensures that even damaged individuals retain future potential for dominance. Predator-prey dynamics along the seabed are shaped by the lobster's presence. Sea stars that feed on bivalves must contend with the risk of encountering a lobster capable of crushing their calcified arms. Crabs, often competitors for similar prey, may find themselves outmatched in direct confrontation. Fish, such as cod and haddock, prey on smaller lobsters, But as individuals grow, fewer species can challenge them directly. The slow accrual of size and strength alters ecological positioning over time. Juvenile lobsters hide within narrow crevices, while adults occupy more open territories, secure in the knowledge that their claws confer substantial defense. The lobster's sensory world is mediated through antennae and chemoreceptors. Chemical signals in the water inform it of prey presence, rivals, and potential mates. The ability to detect faint traces of amino acids released by injured organisms allows lobsters to locate carrion or weakened prey from considerable distances relative to their size. In this sense, the crusher claw is guided by information acquired through sensory systems attuned to chemical gradients. The convergence of detection and pressure defines the lobster's predatory success. Seasonal rhythms also influence behavior. In colder months, activity may decline as metabolic processes slow. During warmer periods, molting and reproduction become more frequent. Females carry fertilized eggs beneath their tails, aerating them with rhythmic movements until hatching. Larval stages drift planktonically before settling to the seabed, beginning a life defined by gradual accumulation of strength. Mortality rates in early life are high, yet those that survive to maturity embody resilience forged through successive molts. Human interactions with lobsters have reshaped coastal ecosystems in subtle ways. Harvesting often targets larger individuals, potentially altering size structure within populations. Management strategies aim to preserve reproductive capacity by setting minimum size limits and protecting egg-bearing females. Such measures acknowledge the importance of longevity in sustaining populations. The slow building power that defines the crusher claw also underscores the vulnerability of a life history dependent on time. As twilight filters through kelp fronds and the current slackens, the lobster resumes its measured patrol along the seabed. Antennae sweep forward, sampling invisible trails. The crusher claw hangs heavy but ready, a testament to years of incremental growth. Nearby, a snail grazes algae on a rock surface, unaware of the pressure that may soon descend upon it. The lobster approaches with no fanfare. There is no sudden burst of speed, no theatrical ambush. Instead, there is placement, alignment, and compression. The shell cracks with a sound too subtle to travel far in water, thick with other vibrations. Within moments, the snail's defenses are rendered irrelevant. In this cold, patient ecosystem, brutality is expressed not through spectacle, but through accumulation. Each molt adds capacity. Each year strengthens leverage. The lobster embodies a form of lethality that matures with age, transforming time itself into a weapon. The crusher claw does not rely on surprise or venom, but on pressure applied with certainty. In the quiet spaces beneath kelp and rock, where growth unfolds slowly and survival favors endurance, the lobster's power stands as a reminder that strength can be cultivated over decades, and that in the deep arithmetic of the seabed, compression often triumphs over speed. Far below the reach of sunlight, where the ocean transitions from blue to an absolute and endless black, pressure replaces light as the defining force of existence. At these depths, cold is constant, currents move slowly, and the only illumination comes from living organisms themselves. Bioluminescent flashes flicker briefly and vanish, small chemical sparks in a universe of darkness. The water is dense and heavy, pressing inward from every direction with a weight that would crush surface dwellers in an instant. It is here, in this abyssal realm, that the squid becomes something more than a familiar coastal hunter. It becomes an embodiment of grip, an organism engineered not merely to seize prey, but to ensure that once seized, escape is mathematically improbable. The deep-sea squid's body is built for a life suspended in 3 dimensions. Its mantle is streamlined and muscular, capable of rapid jet propulsion that allows sudden bursts of speed in otherwise lethargic water. Fins along the mantle provide subtle adjustments, stabilizing movement when hovering. But the true instruments of dominance extend outward in the form of arms and tentacles, each lined with rows of suction cups. At first glance, these cups appear as simple adhesive structures, circular pads that adhere through negative pressure. Closer inspection reveals a more formidable architecture. Embedded within many of these suckers are chitinous rings, hardened into sharp, inward-pointing teeth. These rings are not decorative ridges. They are gripping mechanisms evolved to resist the struggling torque of captured prey. When a squid detects movement in the dark, it relies on a suite of sensory adaptations tailored to minimal light. Its eyes, among the largest relative to body size in the animal kingdom, are optimized to detect faint contrasts and bioluminescent signals. In some species, the eyes are asymmetrical, one oriented upward to scan for silhouettes against dim surface glow, the other downward to detect faint flashes below. This visual system transforms sparse photons into actionable information. Additionally, mechanoreceptors along the arms detect vibrations in the water, subtle disturbances created by swimming fish or drifting crustaceans. In the abyss, perception is less about seeing shapes clearly and more about interpreting disturbances against a background of near stillness. Ambush in this environment is a matter of patience. The squid may hover nearly motionless, adjusting buoyancy with internal ammonium-rich fluids that reduce density and offset the absence of a gas-filled swim bladder. Unlike bony fish, which regulate buoyancy through gas compression and expansion, squid achieve neutral buoyancy chemically. This adaptation allows them to remain suspended without constant muscular effort, conserving energy in a habitat where food can be scarce and unpredictable. When prey approaches within range, the squid's tentacles extend with explosive acceleration, driven by elastic recoil and muscular contraction. The motion is swift and precise, closing the distance before the prey can fully process the threat. The first contact is made not with the beak, but with the suckers. As the tentacles wrap around the prey's body, the suction cups engage, creating negative pressure against flesh or scales. The chitinous rings press inward, and the tooth-like structures bite into tissue. This is not a gentle adhesion. It is a mechanical interlock, hundreds of circular gripping surfaces anchoring the prey in place. The comparison to circular saws is not hyperbole, but metaphorical recognition of the serrated edges that dig inward, preventing lateral movement. Each sucker functions as an independent clamp, and together they form a network of restraint that distributes force across the prey's body. The brutality of this grip is compounded by the squid's beak, hidden at the convergence of the arms. Once prey is secured, the beak delivers a bite that can pierce scales and muscle, injecting digestive enzymes that begin breaking down tissue. In some species, venom plays a role, containing neurotoxins that immobilize prey further. However, the primary assurance of capture lies in mechanical control. The prey is held firmly while the squid feeds, often alive in the initial stages. In the abyss, where there are no witnesses and little chance of rescue, the struggle unfolds in silence. Scars on the skin of deep-diving predators such as sperm whales reveal the potency of these suction teeth. Circular marks arranged in patterns testify to battles fought in darkness, where whales pursue giant squid and are met with a barrage of gripping arms. These encounters demonstrate that the suction rings are not merely tools for small fish, but capable of anchoring into the thick skin of massive mammals. The whales may ultimately prevail through size and endurance, but the scars endure as physical evidence of the squid's defensive ferocity. In these confrontations, the abyss becomes a battleground defined by grip and drag, rather than by speed. Drag itself is a strategic component of squid predation. By anchoring prey with multiple arms, the squid can resist thrashing movements that might otherwise dislodge a single point of contact. The distributed attachment reduces the likelihood of tearing free. Each sucker contributes incremental holding force, and collectively, they create resistance greater than the sum of individual grips. This distributed strategy reflects an evolutionary understanding of hydrodynamics and muscle leverage. The prey's attempts to swim away increase tension across the arms, tightening the hold. Escape becomes increasingly unlikely as energy dissipates against the squid's anchored embrace. In abyssal ecosystems, food webs are sparse but interconnected. Squid occupy mid to upper trophic levels, preying on fish and crustaceans while serving as prey for larger predators. Their rapid growth and relatively short lifespans in many species contrast with the slow pace of deep-sea life. This fast life history allows them to exploit transient resource pulses, reproducing quickly before falling to predation. Their role is both predator and prey, a duality that reinforces the necessity of effective capture mechanisms. The suction teeth are not ornamental excess, but evolutionary insurance in a habitat where missed opportunities may not be replaced soon. Bioluminescence occasionally illuminates these interactions. Some squid possess photophores that emit light, used for camouflage through counter-illumination or to startle prey. By matching the faint glow from above, they erase their silhouette when viewed from below, blending into residual surface light. In total darkness, even minimal light manipulation can mean the difference between detection and invisibility. Thus, the squid's approach may be unseen until the moment of contact, when arms close and the abyss reclaims its silence. Reproduction in many deep-sea squid species involves elaborate mating displays and the transfer of spermatophores via specialized arms. Eggs are often released into the water column, drifting before hatching into planktonic larvae. These early stages rise closer to the surface where food is more abundant before descending into deeper waters as they mature. This vertical migration exposes them to different predator assemblages at each life stage, shaping behavior and morphology. Those that survive to adulthood carry forward the structural advantages of their species, including the chitinous rings that will define their feeding success. Temperature stability in the deep sea means that thermoregulation demands are minimal compared to surface dwellers. However, the cold slows metabolic rates, necessitating efficient feeding when opportunities arise. Squid must balance energy intake with the costs of propulsion and hunting. Their grip-centric strategy minimizes chase duration and reduces the risk of prey escape. In an environment where energy budgets are tightly constrained, this efficiency is critical. As the abyss settles back into stillness after a feeding event, only drifting fragments and faint disturbances hint at what occurred. The squid retracts its arms, the tooth-lined suckers releasing their hold as digestion progresses. Darkness resumes its dominance, swallowing movement and memory alike. In this realm, brutality is expressed through certainty of capture rather than spectacle. It is the relentless assurance that once contact is made, escape is statistically unlikely. The squid's suction teeth represent an evolutionary answer to the challenges of three-dimensional hunting in perpetual night. They convert soft tissue contact into mechanical imprisonment, turning the fluid medium of water into a field of restraint. In total blackness, where vision is limited and distance deceptive, grip becomes truth. The abyss does not reward hesitation or inefficiency. It rewards those who can seize, hold, and consume without wasting motion. In the cold silence of the deep, the squid embodies that principle with hundreds of chitinous rings, each one a testament to the power of grip in a world where light never arrives.